Okay, so let's start with the next part of the discussion in the process of understanding the real-time systems, its hardware and software aspect of it. Okay, so the objective of the today's discussion is to understand how does shared resources are supposed to be used and what are the related issues those are being anticipated when you make use of the shared resources. And after learning this, you should be able to understand and should be able to use these shared resources judiciously. So what this word judiciously means, this is what we are going to have the discussion throughout this next 45 minutes. Okay, so let's start. So we were discussing about the granularity of an application, where this granularity, I am getting some chat messages. Okay, Siddharth, no issues. Fine. Please be attentive now. So this granularity, design of the granularity is itself a tall order question when we think of designing of this real-time or embedded systems. Okay, so why do we consider so? That we are going to discuss in the very first section of this particular discussion, where the design consideration about the granularity of an application is to be thought of. The second, when we have got multitasking, or when you have got more number of tasks to be there in picture, it is never been the case that every task would be assigned its own exclusive resources. We know that resources are getting shared. Rather, they had to get shared. So what are the reasons, what are the benefits of getting resources shared? That is also we are supposed to understand in the discussion of why and how the shared resources or shared data is supposed to be used for it. Then when we are sharing this particular data, what are the problems those are being associated with it? And there are very interesting problem that comes up with it. With an example, we are going to see these particular problems along with its very significant characteristics of it. And then we will discuss about what are the different preventive methods those are being there for in order to resolve the shared data or shared resource problems. When we are saying it's a prevention, there is enough reason to believe that the avoidance or concealment techniques over this particular shared data problem is not of that much use. That is what it is with the saying that prevention is better than cure. We will have to go with the preventive methods of shared data problem. Why is it so? That we are supposed to understand in the next discussions of it. Then, as one of the usage of the semaphore is to, in order to resolve or in order to get rid for the shared data problem, we'll see how these semaphores are getting used for this particular shared data problem, resolving issues of the shared data problem. Then when we are using a multiple semaphores, how the usage of that multiple semaphores is to be made, and because of which some issues like priority inversion arises, and how that particular priority inversions would be taken care by a priority inheritance protocol. So this is what the discussion that we are supposed to make in the today's discussion. The baseline agenda of discussing it is whenever you are designing a software, you are designing an architecture for a software of real-time system, then we are coming out, or we are bounded with the n number of tasks to be used in our application. We are bounded with sharing the resources, sharing the data among these particular tasks. So how we are supposed to make use this particular scenario in the programming in order to get maximum benefit, or in order to not get caught because of these particular problems when we are sharing the resources among n number of tasks. This is what the bottom line agenda of this particular discussion. Okay, so let's start with the discussion. As I told you that, like, granularity design, that happens to be an important consideration. So we are defining the embedded system design with a 2 granularity level or 3 granularity level, right? We call that as an coarse granular design, fine granular design, and medium granular design. What do we understand by granularity? How many number of tasks should be there in order to cater an application, or what is the level of fragmentation of an application you are making in terms of n number of tasks. So depending on that value of n, whether that value of n happens to be less, we call as an coarse granular design. If value of n That is the task that you are, or application you are dividing into n number of tasks. This n happens to be more, we do call that as a fine granular. Okay, and if that happens to be in between a very small and very high, then we do call that as a medium granular. Okay, the better example to understand the real life example is the sugar that we eat is referred to be as a coarse granular, as against of the talcum powder that we used is referred to be as a fine granular. Okay, these are the like examples from which you can understand what we are talking about at the moment for granularity. Okay, fine. So when we have the more number of tasks, when we divide an application with more number of tasks, then what are the different advantage and disadvantage with this? We can understand this very quickly in a way. Initially, we'll start with what are the advantage of having more number of tasks in an application. In the advantage part of it, the very significant advantage that happens to be, and according to me, this is a prima facie advantage, because every embedded programmer, every real-time system developer is expected to establish the control over the response time of an application. And response time of an application, getting control over the response time of application is through getting control over the response time of an individual task, right? So more the number of tasks that you have in your application, the probability of establishing a good control over the response time of an entire application, that chances are very high. That is what in the very first, or as a prima facie advantage, as I told you, that more number of tasks are always better for in order to establish the control for a relative response time. And we are getting good response for the higher priorities in that way, because we are making a priority based preemptive kind of systems in most of the designs of real-time system. That is what whatever the task that we are defining with a higher priority, those tasks would definitely get a good response time when we have more number of tasks to be there in an application. The second obvious advantage that it would come is more the task, more the system is modular. And needless to point here, the modularity always helps in defining a code to be a cleaner code. A cleaner code in a sense, defining the code to be cleaner as well. It is very easy to have the debugging of this particular code, or it gives you some kind of relaxation in debugging of the code when you are defining it as a module wise. And that is what this more number of tasks creates more number of modules, and it gives you this particular better control. Okay, and very like even one more important aspect is the data encapsulation that would be done in more effective fashion. Okay, more number of tasks means you can have the data to be encapsulated among this particular task very effectively, as against of having less number of tasks. Because when you have got less number of tasks, this data encapsulation again becomes the matter of shared data problems. Again becomes the matter of sharing of the data. And when you have got the encapsulation of the data, then during that time, it might not be that much feasible to share that encapsulated version of the data among the different tasks. And that is what, when you are intent to have the encapsulation of data in your application, it is always better to have more number of tasks in the applications. So after discussing this advantage, second side of the coin is the disadvantage that we will have with n number of tasks. That is disadvantage that we will have with a more number of tasks in my applications. Okay, fine. This particular disadvantage happens to be, for example, with more tasks, it's likely to have the more shared data. Now, this is something which is very interesting. So processor loses time in handling semaphores and related bugs, because more the number of tasks, as we see that we had to share the data, we have to share the resources. So when we are sharing the data or sharing the resources, and when we have more number of tasks, those are sharing those particular resources, the chances of getting data corrupted, the probability of chances of getting data corrupted is always very high. So that refers to be as one of the disadvantage when you have more number of tasks in a multitask application, or when you have got more number of tasks, or when you are defined to have the fine granularity with it. Okay. Second disadvantage or second drawback that is very obvious is when you have got more number of tasks, you are likely to have the inter-process, inter-task communication to be even extensively. That is what you need to make use of more number of queues, more number of mailboxes, more number of pipes in order to establish the communication among the tasks when the number of tasks are very high. So there might be a mapping of 1:1, 1:many, many:1. So depending on the communication model that you might design in your application, you might need to make use of more number of communication primitives from the operating system when you have more number of tasks. Okay, so this comes as an allied drawback. This comes as an allied requirement. Rather than drawback, I would put it in a way allied requirement. And this requirement later on becomes a drawback in terms of not able to manage the volume of the inter-task or inter-process communication. And that is what specifically it is getting referred to be as a drawback. Okay, so it looks onto the completely perspective on in what way we are taking this particular drawbacks. Okay, if we take this drawback as in challenges, definitely we would definitely flourish with the more refined version of the designs. Okay, but as an entry level designer, this definitely seems to be as in challenges. That is what referred to be as a drawback in the literature. Okay, then more number of tasks, we understand each task is expected to have its own stack. And that is what, if you have got more number of tasks, you have to define each task for the, or the task for stack for every task. And that is what you end up in defining more number of stacks. And that is what the utilization of the RAM that also becomes very bulky, isn't it? And that is what the reason, like it is said, it is referred to be as a drawback for it. Because RAM is not the luxury that we all know in the embedded systems. It has to be made use of in a very judicious fashion. And that is also one of the consideration, I would say, in order to define how many tasks a specific application should have as a multitasking application. Okay, fine. Then time consumed in saving and restoring the context is very high, that we know. When we have got more number of tasks, we land up in more number of task switching. When we land up in more number of task switching, definitely the amount of time that will be required for task switches, that would also keep on increasing. And as I always refer, that task switching time is referred to as an overhead. This is referred to as an overhead time, which directly does not contribute to the functionality of an application. And that is what we say, it's an overhead time. And for any system design, overhead time is expected to be minimized. And that from this particular perspective, more number of tasks as requires more number of context switches to be made in the process of task switching, we will end up in having more time to be consumed in saving and restoring the context. And that is what the overhead would become heavy, overhead will become high. That is what referred to be as in one of the disadvantage of this particular having more number of tasks for the any applications. Okay, so after this particular discussion of advantage and disadvantage of granularity, let's there is one more disadvantage that is being left out, is when you have got more number of tasks, every task tend to have make use of the calls from the real-time operating system. So when they make use of the call from real-time operating system, as we know, a very famous word, a very famous statement, that there is no free lunch. Operating system provides the service at the cost of its service time. And service time of an operating system is again referred to be as an overhead, because that really does not contribute to the functionality of an application. That is what more the calls that more the task, more the calls that could be referred to the RTOS. And again, the time that it will be elapsed in order to manage the calls to an RTOS, that is also going to be an elevated, or that is also going to be an elongated process. Okay. So after this particular disadvantage, discussing this particular disadvantage, let's move on to understanding of the shared data issues. Why we had discussed this earlier, the fragmentation or the granularity? Because unless and until at the very first stage, we won't able to get understood how many tasks an application should have. Okay, there is no golden rule. There is no rules as such for how many tasks, how many should be the number of tasks for an applications. It depends on the design. It depends on the different aspects that you wanted to get cover, along with the time control, along with the control over the response time, along with ability of the resources that you could use in your system. Okay, and along with the data that you wish to share among the different tasks. Right, and that is what in subsequent we need to discuss about what is the shared data usage and why and how this particular shared data usage is to be used. Okay, so to begin with, let's first try and understand why this data is to be shared. Right, as we say that there can be even one-to-one mapping. Like for example, if I want to make use of some variables, I can define that variable as a local variable to individual tasks. Right. When I'm defining a variable to be as a global variable and allowing every task to use that particular variable, then I'm getting catch into the scenario of shared data or shared variables, isn't it? So why, in fact, I need to have the variables or data to be defined in a global way so that other tasks should be able to make use of it. Okay, there should be some finite advantages out of it. So what are those advantages? Let's discuss those advantages first. Okay, so first advantage that happens to be the optimum usage of the resources. Obviously, when I'm sharing the resources, the number of resources those would be used in order to satisfy the need of an application, those are also getting reduced, isn't it? So that is an obvious advantage that it would come with the shared data. Fine. The second advantage that you would see is the design of dependability. When you're sharing the data, you can definitely make use of the shared data for the communication purpose also. It's not only that that is to be thought to be as a resource, that can be also thought to be, or that even can be thought to be as a communication medium. Like one task writes something into that particular data. When the second task is reading that particular data, so the same shared data, then the second task could get to know the activity happened in the task earlier task, right? So that can be thought to be as a communication methodology. So in an application, as I always say, you cannot have all the tasks to be independent one. There always has the degree of dependency among the tasks that you write an application. So in order to resolve that particular dependency, the design of resolving the dependency can be thought of even with the help of the shared data. So this is again going to be a second allied advantage that you will get with sharing the data in an application. Okay, fine. The third advantage that obviously would get is, or third rather than advantage, I would say the reason or the purpose that to share the data is means of communication among the task, as we have discussed it right now. Okay, then how to use this particular shared data when we are making use it for this kind of purposes, this kind of functions, this kind of, I mean, requirements, then how this particular data is supposed to be used of. Okay, so this particular data is to be used in order not to lose the data integrity. Means data integrity should be intact, and this is the bottom line of how the data, shared data, is to be used. Getting my point? So data integrity means as on when the data, the way in which the data is to be used, or the value of that particular data, value of that particular variable, that should be intact, that should not altered by, the shared resources in a way where it would give some wrong inference, or it should give some wrong significance. Normally, when the data is shared, it is allowed to alter the data, because that is what the purpose for which the sharing of the data is to be used for it. But when it used in such a way that it would create some confusion, or it would create some kind of significance in the logic of your program or in the execution of your program, by virtue of which, even though the operation becomes very successful, end result will not be as it is being desired of. And this is what the typical problem that happens to be as a shared data problem, which we intend to discuss in next couple of slides. With an example, I wish to discuss this particular problem. Okay. And that is what data integrity at the bottom line, as I'm saying, that data integrity has to be intact. It should be intact. What do you mean by data integrity? Let be patient for some couple of slides, then definitely would get to know about this. Okay. Then, as I said you, that the resolving dependency is again one of the we can make use of the shared data, or we should make use of the shared data for resolving the dependencies. Okay, so after finding out, or after understanding why to share the data and how to make use of this particular shared data, let's move on with some example, very famous example, which is being mentioned into the book, as it is being said, as it is being referenced as an embedded software primer by David Simon. So in this particular book, one very interesting example and very simple and lucid example is being given. So what is that example? Let's try and understand that example and understand how does this particular sharing of the data becomes a problem. Okay. And that's referred to be as a shared data problem. So in this particular example, I expect you to just read this particular, or just see this particular example for 20-25 seconds, and then we'll discuss about it. Okay. So in this particular problem, or in this particular example which is being given, you can see that there happens to be the two tasks, and these two tasks are nothing but, one is the main task that I'm writing here as a main application program, and second is referred to be as an interrupt service routine, for example. Okay, and this interrupt service routine, you can see here at this moment, this interrupt service routine, for example, reads the temperature from two channels, for example. Okay, and these temperatures which is being read is expected to be stored into a array of this I temperature with a 0 index and I temperature with an 1 index, and I temperature defined as an array statically with an integer items of 2, maximum length of 2. So the array is being defined. Okay, and the item of this particular array is expected to be updated by reading the values from the hardware. And let's say I have got the two hardwares, two channels, I'm making use of it. And interrupt service routine, when it executes interrupt service routine, it reads the value of from that hardware, independent hardware, and update this particular um, array of this item with an appropriate item of 0 and 1. This is what the interrupt service routine does in this case. In main program, if you see, I have defined the two additional variables called itemp 0 and itemp 1. Okay, and we are comparing these two values of acquisition, two values of temperature, by transferring it to this particular local variable to this main program, which is itemp 0 and itemp 1. Okay, and in a case where item 0 is not equal to item 1, that becomes some kind of alarming system, that becomes the some kind of indication that some corrective action is to be taken up. Means if you refer this application on a gross level basically monitors the temperature from two independent channels, and it is expected in a system that both the temperature should be always constant, or both the temperature should be always same, not constant, always same. And being found the difference in this particular temperature, there happens to be a problematic case generation, and that is to be tackled out with some kind of corrective actions in the further part of application. Getting it? So the purpose of this particular example is to monitor the temperature independently from the two channels. Monitor this in this particular main loop. Whenever it finds that the temperature are going to be different, or temperature found to be different, then in that case some kind of alarming system is to be generated. So this is the simplest application that you can see. So can you see some problems in related with, because you can see that the I temperature, this particular array is shared, this array is being shared among the two tasks, interrupt service routine, and the main task. Means this shared data or shared array of I temperature is being used in two tasks, this interrupt routine ISR and this particular mainline program. Now, what kind of typical problem might arise out of it? So let's investigate that. Okay. So for example, this interrupt has been generated, and as against of this interrupt might be generated in a sampling mode, right? After every 1 minute, it has to check that whether temperature is same or not. So I can plan that particular activity with a periodic interrupt, right? So with this periodic interrupt, let's say I have planned the activity in order to access the temperature from the two channels. Okay, so and this particular temperature of the two channels is being read sequentially, for example. Okay, so interrupt service routine is executed. Let's say that this interrupt service routine has acquisitioned the temperature in the first channel and recorded and or this copied that particular temperature into I temperature 0. Okay, I temperature 0. And let's assume that by virtue of some kind of multitasking, by virtue of some kind of events, this particular interrupt service routine has to get stalled, has to get stopped, and move back onto the main program. So it has updated only this I temperature 0, and the task switching would happen from this particular execution to mainline program. So the earlier value the earlier value of itemp 1, that would be same as that of itemp 1, right? And the new value that is halfly updated, the array is halfly updated, and within the updation of the array, in between that, some interrupt has occurred, some task switching has occurred, and because of which that particular task is not getting a chance to execute, so that the next task would come into picture. So this particular main has to execute for now. So when main executes, this finds that this I temperature 1, which was an earlier one, that is the same value, but modified value is being found into this I temperature 0, right? And I'm making this particular assignment with I temp 0 and I temp 1, and I'm comparing this particular assignment with I temp 0 and I temp 1. So what do you find into this? You'll find that even though the temperature happens to be the same at the instant where the temperatures were acquisized, even though that temperature in a physical phenomenon happens to be the same, my circuit or my program, the way in which the shared data is being used, my program gives me the false howling alarm. This false howling alarm would be rung. And why? Because there is a half updation into this data which is being shared onto it. I hope this particular problem is very clear now to you, right? It is with an assumption, it is with a condition that this particular data, which or this array I temperature is halfly updated. And after updation of the first element, it has made a switch from this. And that is what we are getting this particular problem to be arise with it. Okay. Now, you might say that this temperature 0, temperature 1, because of the local variables, those are being shared. This might be the case, right? So let's say the modified version, as you can see here, in the modified version of this program, what is being done? Everything is being same. Only this particular this local variables which is being there, or local integers which is being there as an item 0 and item 1. So these are not being found into this. So directly it is getting compared. It reduces the risk. It reduces the risk as against of these two, as against of the earlier situation. That is what I'm calling that as a modified version. Okay. So it might be the case that item 0 and item 1 need to be updated. And as they are not being updated, within the way in which this particular program multitasking would happen, the false howling alarm will generate. Means system would give some falsified result of it. Even though the situation is very good, it gives me the result that situation is not good. Okay. Now in the modified version, as I said you that this particular local integers, those are being eliminated. Okay. And directly the array values are compared. When I'm comparing these array values, okay, I'm giving one more, I'm just coming up one more level up in order to get rescue to this particular problem. Okay. And in order to get rescue, I'm giving coming one more level up, by which I'm not making any local variables to be made use of it. And I'm directly comparing the array elements itself. Okay. Now, when I'm comparing the array elements, don't you think that these array elements to be compared in without an interruption? These are to be compared without an interruption, because this particular instruction happens to be a C instruction, right? And we know that every C instruction is expected to be disseminated into n number of assembly instructions. Referring to its usage, it is referred to be as an, or it would get disseminated into the n number of assembly instruction. And if this would have been an assembly instruction, I could guarantee that within the compare operations, interrupt might not be entertained, interrupt might not be generated, or even though it is generated, it might not be entertained. Okay, but being this statement written in C, and as it has got the equivalent instructions in assembly to compare, right? So unless and until whole assembly part is not being guaranteed to execute in a single shot without an interrupt, I again land up in the same problem of having this. So earlier problem is because of the task switching. Now here the problem happens is because of the interrupts. If interrupt comes in between the comparison of the two array elements, then in that case also I might not get the very correct value of it, because by the time when interrupt occurs, the next routine, interrupt service routine, again might get a chance to update these values, and again there would be some falsification in the results of it. Okay, so as this particular assembly instructions is getting divided into an equivalent assembly for the comparison, you can see that, for example, item 0, this is first need to be moved into the R1 register. Item 1, that is second item, is to be moved to this R2. Then I need to subtract this R1 and R2. I need to find out with a result with a conditional instruction, jump if conditional. If it is 0, then temperatures are okay, otherwise they are not okay, isn't it? I mean, these are the equivalent instructions. Those are getting written by assembler or by the cross compiler in order to get the hardware realize what is to be done. Otherwise, this C instruction, how the hardware would get to know what to do with the C instructions, isn't it? So that is what in equivalent assembly, if you see, this one statement of C boils down to n number of assembly statements. And here you cannot guarantee that the interrupt will not be generated until it completes everything. Okay, interrupt might get generated at this moment, at this moment. So you cannot guarantee that this interrupt will not be generated within the particular instructions. Okay, assembly interrupts are getting deferred till the the current assembly instruction is running on. This is what we understood, right? If the assembly instruction is running, in between that, if interrupt comes, then the assembly instructions are allowed to execute till the end. Okay, so within an assembly instruction, if it gets, then definitely there is no issues, because that would get executed within its time frame. But in a set of assembly instructions, which is equivalent to comparing of the two array elements, if something goes, some interrupt comes in between this, then there is no scope that this has to live in between and has to go to the different ISR of it. Getting my point? So even though we are trying to reduce these local variables for comparison, the language or the language that we are adhering in order to compare it, the elements from the shared data, that would becomes a problem. And this is specifically referred to be as a shared data problem. That is, unless and until the complete data or the data which is being shared is not being updated in its holistic fashion, until it is not being updated in a specific time span, or without an interruption, rather more to correct it, without an interruption, you will not be able to make use of this particular shared data very effectively or very judiciously. This is what we refer to be as a shared data problem with this example. Okay. Moving on next, what are the characteristics? Now we understood this particular shared data problem, right? Now, what are the characteristics that we find for this shared data problem? So there is only one characteristics which is a significant one, and that characteristics happens to be that this particular shared data problem, occurrence of the shared data problem is highly unpredicted. It's highly unpredicted. And that's what it is being written, that it is just like as an Fendish species. You never know when those are going to be taken in birth. Okay. And that is what referred to be as a highly unpredicted. Because you never know when that particular shared data problem would come. It would not be the case that all the time when it runs, it will, like for example, 1,000 runs of your iterations, 1,000 iterations of your program, it might not pop up. And maybe it would pop up at 1,000 first time of the iterations. I think there is a very high uncertainty. There is high unpredictability of arising of this particular shared data problem. And when such kind of events are being there, as we always discuss, that prevention is better than cure. Because you never know, you cannot anticipate, you cannot predict the arrival of the shared data problem. And that is what it has to be taken within preventive methods of it. Okay, so we'll see that preventive methods in the next slide. But at this particular moment, in order to just give a feel like what kind of unprediction and what happens because of this unprediction, the author David Simon has given very nice examples at the moment. Okay, so what are these examples? Let's say that this particular problem would arise at 5 o'clock in the evening on Friday. I think the significance of the statement is understood to you, right? Saturday, Sunday happens to be on holiday. And if we are getting caught with this particular problem and 5 o'clock is expected to be as an end time of an office hour, right? So at 5 o'clock, at the fence of the 5 o'clock, if this particular problem occurs, then no one would be there to attend that problem. And that problem is expected to be sustained for next 2 days. That means it's highly unpredicted. And if this problem occurs at this particular time, that will not be getting attended. Okay. Second example is anytime you are not paying very much attention in a lethargic mode of the operations, that might happen. And if that problem pops up, then it becomes a problem for us, right? Or when no debugging equipment is attached to the system. If it expect to go into the auto recovery mode, such kind of debugging systems are being there into it, then it's okay. Otherwise, if it is not being there, this shared data problem would cause some problems, really some problems of it. Okay. Or very interestingly written that after your product is landed on the Mars, thousand millions of trials are being there on the Earth. Every time it works very accurately, and the instance at which this particular product is being landed on the Mars, that shared data problem might pop up, and you might not get any chance to recover out of that particular problem. Next is during customer demo, or you can refer that during the project demo. Everything finds very well till you comes to the point of demonstration to the examiner, external examiner. And during that only it comes like, only at that point if the problem pops up. Why? Because there is heavy uncertainty, there is heavy unpredictability. So unless you are not being taken a cover of it in the beginning in the form of prevention, you are always being there in a mess, you are always being there in a potential threat of occurring this particular problem at any point of time. And all these examples are being just an exemplary illustrations of highly unpredictable nature of this particular shared data problem. Okay, I think this much discussion is sufficient to understand the characteristics of this particular shared data problem, which is unique, which is highly unpredicted one. Fine. So what is the solution of it? The solution of it is, don't expect that problem to occur and then you will have some kind of concealment or some repair kind of actions to be there. That would be too late for it, right? As against of that, I need to make sure that some kind of avoidance or some kind of prevention methods are to be used in order not to get caught with this particular shared data problem. Okay, what kind of prevention or this avoidance methods are being there? Let's see it very quickly now. Okay, so prevention methods of the data, like you, by the discussion that we made till this point, you might understand a very significant activity out of it. What if you want to make use of that shared data? You have to make use of that shared data in a way where the shared data updations or shared data usage is to be made into uninterrupted fashion. Okay, if that is being made into that is being made use in an uninterrupted fashion, then this particular problem will not get a chance to exist itself. And that is what the prevention or avoidance method is being referred of. In what way? Fundamentally, the section which you want to get an updated as a shared section, that has to be made an atomic or critical in order to rescue from the shared data. The word atomic indicates that there shouldn't be any further fragments onto it, isn't it? That is what it has to be, without an interruption. That is what the word atomic is being used in this particular literature. Okay, and what if you identified that this is a critical section, that is a potential threat section where you want this entire section to be executed without an interruption, then you define that to be as a critical section and use that and make some provisions by which the critical sections will be executed without an interruption, isn't it? That is only the way where you can find out that you are trying to prevent, you are trying to avoid the potential problems with shared data. Getting it? Now, in order to do that, when I'm saying that the critical section and it is to be used in an atomic way and all that, we'll have to first of all understand what are the reasons because of which this particular threat or this particular problem would arise. Okay, as we've seen in the example, this particular problem arises because of arrival of the interrupt. This particular problem would arrive when you have got some kind of multitasking is facilitated, and because of the task switching, that particular problem might be popped up, isn't it? So, and one more interesting thing is when you are using this in a non-atomic fashion. Okay, so if you see fundamentally the reasons because of which this would take place, if you could take care of those reasons itself, if you try and eliminate those reasons itself, then definitely it is said to be as a method of prevention or method of avoidance. So with that particular logic, how this is to be done? First of all, with disabling and enabling an interrupt. How? Whatever section that you are defining to be as a critical section, you wrap this critical section with the enabling and disabling of the interrupt, so that whenever that section is to be executed, disable the interrupt so that interrupt will not be entertained, and after just immediately completion of that particular section, you can enable the interrupt so that interrupt will also be given a justice. So interrupt would be given a half-hearted justice in a way that it's never being all the time entertained at the arrival of it, entertained at the request time of it, but these interrupts in this particular critical case is expected to be delayed in time. What is the amount of time? The time for which this particular critical section would execute. And this particular concept of gross concept of interrupt disabling is referred to be as an interrupt deferring. There's a concept in the embedded system called as an interrupt deferring. Disabling is, we understood that we disable the interrupt. Okay, in deferring, we principally agree to disable it for that amount of time. Okay, and after that particular critical section is being over, you are supposed to make it say enable. And that is what we said, that interrupts are deferred, they are not denied. Okay, interrupts are not being denied, they are deferred in time. And that is what the concept that we call to be as an interrupt deferring. And as I said you, the cause because of which this particular problem would arise, we have valid reasons to cut that cause itself. And that is the first method, as we are saying, that we can enable and disable the interrupt, wrapping of it. The second reason is because of multitasking. Multitasking happens because of the scheduler, and every operating system gives you a facility to lock the scheduler and unlock the scheduler. So before entry of critical section, you can lock the scheduler so that multitasking will not be there till that particular critical section executes. And at the end of that particular section, you can unlock that scheduler. So you can wrap that particular section in the locking and unlocking of the scheduler. The third method is by making use of the semaphores. Semaphores are already being discussed in the earlier chapter with its usage of the resource synchronization, usage of the mutual exclusive access of the resources. Okay, and very well in line with that, this particular semaphore is also being used in order to protect the section, critical section, not to get interrupted with. Okay, so if you see this, same example, if I carry out in order to demonstrate how to do this, then it goes in this way. This is an example that we have seen, right? Now, here, this is the section which has to be updated in a critical fashion, which has to be updated in an atomic fashion. So if I wrap this particular section with a pair of enabling and disabling of the causes of that particular either an interrupt or multitasking or some methodology by which I can have sync of mutual exclusive access to this particular resources. Okay, and this goes in this way. So before entry of this critical section, I can go with disabling of interrupt, or I can go with the locking of the scheduler, or I can keep on reserving, I can taking a semaphores, okay, so that this when I take a semaphore, as we know that the other task which is waiting for semaphore cannot be you making use of this particular the or updation process of this from the task, right? And once this updation is being done, you are free to enable the interrupt. So interrupts are deferred, not denied. Okay, or you can unlock the scheduler so that the multitasking will start once again, or you can release the semaphore so that the task which is being waited for semaphores that can make use of this particular critical section. So what in all we are trying to have? We are trying to avoid, we are trying to prevent the access of the shared resources from the other task and trying to give an access in a mutual exclusive fashion. And this is what the key that we said to be as an offering the sharing of the data with a preventive methods, with an protocol, or this called as an avoidance protocol methods. Getting it? So this is what I wanted to make sure that you understand, that there are preventive methods rather than corrective methods. If you make use of these methods, then there are no fear of having this data, though you are shared it, you don't have any threat, or so to call that future threats or potential threat that would be generated even though the data is being shared for it. Okay, so this is what in nutshell we need to understand as the sharing of the data, the shared data problem, and the prevention methodology of this shared data problem. Okay, this is what we have illustrated with a very simple